So, good morning to all the participants. Welcome to this session on the static single assignment form and its applications. So, why do we need yet another form called the SSA or the static single assignment? The answer is, the number of optimizations possible in a compiler is quite large, and not all the optimizations can be done very well on the quadruple form that we have looked at. So somewhere in 1990, the some of the people from IBM, they discovered one more intermediate form, which is the static single assignment form. The most important property of this static single assignment form is that every variable has exactly one definition in the program text. So we must read text, properly, fully. The reason is this does not exclude any loops. It doesn't mean there are no loops. Obviously, the program must have loops. Otherwise, there is not much we can do. This is a static single assignment. So in other words, by looking at the text, you will see only one assignment to each variable. And it is not a dynamic single assignment form. Okay. So we will know very soon what this really means. Then the flow of control remains the same as in the non-SSA form. The one extra specialty is that there is a merge operator called phi, which is used for the selection of values in join nodes. This will also become very clear with an example. And the main reason why we want such a form is that some compiler optimizations are better on the SSA forms. Two examples which stand out are the conditional constant propagation algorithm and the global value numbering algorithm. So we have seen the value numbering algorithm on basic blocks. In fact, we are stuck with just basic block level optimization using value numbering because it's not possible to extend it meaningfully to the complete procedure or something like that. Whereas with the static single assignment form, larger pieces of code can be brought under value numbering. We will see that how exactly it happens. Then the conditional constant propagation algorithm that we use for with quadruples and so on, it has its limitations because there are many variables which are assigned many times and so on and so forth. So with the single assignment that is possible with the SSA form, we will see very soon that the conditional constant propagation becomes much faster. And of course, it can discover sometimes a few more constants. Not every time, but sometimes. Here is a very simple example. On the left side here is the program, the normal program. Okay. And on the right side here is the static single assignment form for this particular program. So the control flow graph is as usual. So read ABC is as usual, nothing special. And the condition check A greater than B is as usual. And then the A greater than C is also as usual. Then starts, the difference, right? So if A greater than C, we say max equal to A. If A is less than or equal to C, then we say max equal to C. Since we have to assign each variable only once, we have said max 1 equal to A here and max 2 equal to A. in the else part. Similarly, the B greater than C also has max 3 equal to B and max 4 equal to C. When we want to print the value of max in the program, well, we had only one version of max. It accumulated the maximum and we could print it out happily. But here, look at this. There are 4 versions of max. So which one is relevant? That's the question. So, but it is very clear that only one version will be relevant at runtime. So if the control flow arrives along this path, then max 1 is relevant. If the control flow arrives along this path, then max 4 is relevant. Similarly, for the other two paths, this and this, max 2 and max 3 will be relevant. So with this, property in mind, the SSA form introduces a choice operator phi. So the semantics of phi are fairly straightforward. There are as many, parameters as the number of incoming arcs to this phi box. So there are 4 incoming arcs here. So there are 4 parameters for this phi box. Then when at runtime, the semantics of the phi statement would be, if the control arrives along the first edge, then pick the first parameter. If the control arrives along the second edge at runtime, then pick the second parameter, and so on. In this way, exactly one of max 1, max 2, max 3, max 4 would be chosen. So the semantics of the entire program would remain the same. And one of these, which is chosen at runtime, will be assigned to max 5. Now you can simply say print max 5. So when you print max 5, you get the same value as max here. This phi operation is special. The operator is special. It chooses one of the parameters depending on the incoming arc through which control flows. So that is the semantics of the phi operation. Is there any question so far? So now let us look at a program which has a loop. So this is the normal program and this is the SSA form. So immediately you can recognize a lot of differences. So here is I equal to 0 and then we have I equal to I plus 1, right? So there are 2 assignments in the original program, but then we have 3 assignments in the SSA form. I1 equal to 0, then I2 equal to phi of I3 comma I1, and then I3 equal to I2 plus I1. Okay, so it will be very clear why this is required. Then the rest of it is quite straightforward. Read of n1 is read of n becomes read of n1, and this n not equal to 1, that comparison, on which variable should it be carried out? Like in the previous example, we had to choose one of max 1, max 2, max 3, max 4. Here also, we have to choose, either the n which comes from the top or the n which is actually being assigned here and brought via the loop. So there are 2 values of n which come out and one of these has to be chosen. And that necessitates a phi operation for the n. So we have n2 equal to phi of n5 comma n1. n5 is here and this is the value which goes up. and N1 is here, which is the value which comes from the top. One of these two will be chosen based on the edge which is taken for the control by the control. And exactly the same thing happens with I also. So when we actually come from the top, the value of I1 is relevant. And when we come from the bottom through the loop, the value I3 becomes relevant. So we have a phi statement which chooses the appropriate value of I. That is assigned to the variable I2, and I2 will be used in this place. Right? So that's and of course here also it will be used here as well. So there is a N3 and another N4 which are assigned here, and they correspond to these two N operations, N variables. Again, we have exactly the same situation at this join. We have N3, we have N4, and which of these is relevant actually depends on the edge which is taken, at runtime. So because of that, we require one more phi operation which chooses either N3 or N4 based on the control flow. And that value is assigned to N5, and that is used for further operations. So I have only described the form of the SSA. What exactly its semantics are, I have still not told you how a normal program can be converted to the SSA form. I can only give you a brief overview of how the conversion happens because the details are quite complicated. So before we proceed with the conversion, is there any question? Okay. So to understand the conversion process in some detail, we need to go through a couple of definitions. And one of them is the definition of what is known as a join set. So if S is a given set of flow graph nodes, the set join of S is the set of all nodes N such that there are at least two non-null paths in the flow graph that start at two distinct nodes in S and converge at N. So the picture should tell you, explain this quite easily. The set S is A, B, C, D, E, right? These are the elements of the set S. So let us pick A and then E and then D, right? Three distinct elements of the set S. Now there are paths from A, another path from E, and a third path from D, which converge at G. And there are no other common nodes among these. Okay, so that's another important condition that is stated here. Similarly, if you consider the two distinct nodes B and C, they converge, they have paths which converge at F, okay, with no other common nodes. Therefore, the join set of S is said to contain F and G. So we actually, the way we do it, we will take two of these A and E, then see that they converge at G. Then we can take A and D, that also converges at G. Then we take E and D, that also converges at G. If you take A and B, they don't converge at any point. If you take A and C, they don't converge at any point. So this pairwise checking will, by hand, we can compute the join set. Okay. then the something like a closure has to be applied on the join set, and that is called as the iterated join set. So join 1 is join, and join I plus 1 is join of the original S and the join I of S. Okay, ith join. So if you join S and join I, if you join S, combine S and join of at the ith level, and then apply join again, it may give you a few extra nodes in join of I plus 1. So I will tell you why this may happen. Now why are we doing all this? Why this machinery? So let us say S is the set of assignment nodes for a variable V, right, in the program. Then join plus S is precisely the set of flow graph nodes where the phi function is needed for V. So that is the significance of the join plus set. And this join plus is called as the dominance frontier, and there are very efficient algorithms to compute it. It is not necessary to compute it the way I was showing it to you by hand. There are efficient algorithms to compute it. So this is how here is an example. The same control flow graph. So if you consider the variable I, it is assigned in B1 and it is assigned in B7 also. So our S will consist of B1 and B7. Now what is the join plus operation on B1 and B7? So you take B1 and B7, they actually converge at B2, right? So B2 will be included in the join plus set. If you actually put, B2 also into the set and say, let us compute join of B1, B2 and B7, well, it is very easy to see that there will be no change. The only place where convergence happens is B2. So I told you that there is a reason for iterated join. The point is, when we insert the phi instruction after the first iteration, it is possible, and that would be an assignment to a variable that you have seen already. It is possible that the new assignment actually induces another phi instruction somewhere else. That is the reason for taking the join plus rather than just the join. In this case, of course, both the join and join plus are the same, but with a slightly more complicated example, we can cook up something which shows that introduction of a phi instruction will induce one more phi instruction into the program. This is the reason we need a join plus. Now let us consider the variable n. It is assigned in B1, it is assigned in B5, and it is also assigned in B6. 3 of them. So we have our S as B1, B5, and B6. So if you consider B1 and B5, B1 and B5, the place where they actually merge or converge is B2 again, right? So this comes here and this goes there. Similarly, B1 and B6 also merge at B2, very clear. And B5 and B6 will merge at B7, right? So now you add these into this and try to iterate. Well, you don't discover any extra. You will still get the same B2 and B7 as the convergence points. So our dominance frontier for n is b2 comma b7, and the dominance frontier for I would be b2. So in other words, it is b2 and b7. These are the two places where we require 5 functions for I and n. Okay, not both of them in both places, but that would be decided anyway. No problem. Any questions? So let me now give you an overview of how the minimal SSA form is constructed. So compute the dominance frontier for each node of the flow graph. Keep it aside. Now take each variable v and place trivial 5 functions. I will tell you what trivial 5 functions are very soon. In the nodes of the flow graph, using the algorithm place 5 function, that is here. What does that say? The 5 placement algorithm picks the nodes ni with an assignment to a variable. Okay, take that and now place the trivial 5 functions in all the nodes which are in the dominance frontier of the variable. That's all. So take a variable, see where it is assigned. For each of those blocks, take the dominance frontier and put the 5 function in those blocks which are in the dominance frontier. That's all. And to make sure that we are computing the join plus instead of just the join, we use a queue work list for this purpose. In other words, once we add a once we decide that a 5 function has to be placed in a node, that node is added to the queue so that we pick it up again for another round of 5 placement. Then I will show you an example of this now. So the dominance frontier is written beside the basic block number. So for example, the dominance frontier of B1 is 5, for B2 is B2, for B3 it is B2, for for this B4 it is 5, for B5 it is B7, here also it is B7, and for B7 it is B2. We have computed it and kept. Now, if you pick up the variable I, it is assigned in these 2 places, right? So what do we do? Okay, for I and B1 combination, there is nothing to do because the dominance frontier is 5. But for I and the B7 combination, B2 is the dominance frontier. So we insert a trivial 5 function here. A trivial 5 function is the one in which the parameters are not yet distinguished. They are the same, I comma I. It is not I1, I2 or I3, I4, etc., etc. We will do that in the next step. Now, B2 itself does not give you anything extra because B2's dominance frontier is just B2. So iteration does not give you extra. Now take the n. Again, B1 and n do not yield anything. Now B5 and n yield B7. So we have a trivial 5 function inserted here. B6 and n again give you the same B7 and we insert the 5 function here. Now we have a 5 function in which there is an assignment to n. So now we add B7 into the queue. Now what happens? The dominance frontier of B7 is B2. So what happens is the 5 function, trivial 5 function gets inserted into B2 also. See, that is how the second iteration inserts the 5 function into the basic block B2. And that's all there is to it. There are no more 5 functions. B2 will not insert any more 5 functions anywhere else. So the insertion of trivial 5 functions is completed. Any questions? The next step is to rename the variables using the algorithm rename variables. I am not going to show you the algorithm, but I will give you a very detailed example. Okay. Rename the variables, the first step. So, is to decide the order in which we traverse the basic blocks. The depth first search order of the dominator tree is the order in which we visit the basic blocks. Okay. So, there are of course very good reasons why this is necessary. So, we define before we, we look at the definition before we look at the uses. That is the reason. So, the first block is B1. So, we visit B1. Now, the definition of I here is renamed as I1. And the read statement is also a definition because we assign to the variable. So, it is renamed as N1. Apart from that, this is the only place where we know that from B1, we will be entering B2 via this edge. So, because of that, we will rename this variable in the phi function and this variable in the phi function as I1 and N1. Because when we arrive from B1 to B2, the control flow, that edge is taken, and therefore the value of I1 and N1 will be relevant. So that is why the renaming function will do that here. Okay. Only for the phi function. Now we visit B2. So we assign a new variable for I2, but please see that this I is not yet assigned a variable name. That will be done later. This definition is also assigned a variable N2, but this N also remains. There is a usage of N here, and that is actually this itself. So we can rename that N as N2. And the visit of the block B2 is over. Now visit B2, B3. Now there is a usage of N here, and the N which is relevant is the current version of N, which is N2. So that is easy. Then we visit B5. There is a new definition, so it becomes N3. But there is an old usage, and that is the N2. And now again, we are coming along this edge to block B7. So it is time we rename this variable as N3. Because this is the only place we know that we are arriving from B5 to B7. Next we visit B6. So this is renamed as a new variable N4. This is still the old variable N2, which is coming from here. And it is time that we rename this N4 because we know that we are arriving along this control flow edge to the block B7. Then we visit the block B7. So this variable here gets a new name N5. This variable gets a new name I3. And this is the old I2. And these two have already been renamed. So no problem about that. But when we are coming along this edge, we know that we are entering via the second control flow edge. So it is time we rename these two variables as I3 and N5. If we miss it, then we won't be able to rename them again. Okay. Finally, we visit B4 and this I2 can be renamed easily. So this is the final renamed version of the SSA form, which we had seen before. So if there are any questions, I can take them at this point. So renaming of variables requires a version stack, as some of you might have guessed. So we need to keep the version of the current version, etc., has to be kept on the stack, and it has to be pushed and popped appropriately. And that will be how to push and pop is based on the dominator tree relationship. Okay, so SSA form, I think it is just a repetition of that picture. Okay. So now we know how the SSA form is constructed. At least we know the outline. So again, to recall, we are given a normal program. Then we get the control flow graph. We compute all the dominators. We take one variable at a time, and insert the phi function according to the dominance frontier. And then we go to the renaming algorithm, traverse the basic blocks in a particular order, and perform the renaming. So after that, the SSA form is ready. So let us look at some of the optimizations using the SSA form. But before that, there is a word of caution that is necessary. It is very tempting to come up with an optimization on the SSA form, which looks very aggressive. It's actually, sometimes it would be incorrect. Okay. Why? Any transformation, optimizing or otherwise, right, on the SSA form must retain a very important property of the SSA form called the dominance property. So what is this dominance property? Every definition of a variable dominates all its users or predecessors of the users in the case of phi functions. So here is a definition D1, and here which says A equal to B plus C. So, and whatever users of A we have here, A. So this node will dominate all these three nodes. That's what we are saying. And this is a very important property of the SSA form. And this is guaranteed at the time of construction. Okay. And any optimizing transformation must make sure that after the transformation, the dominance property is retained. So if that is not so, then the transformation is incorrect. Okay. So with that in mind, let us start looking at some of the simple optimizations. The first one is the dead code elimination. We have seen dead code elimination in the case of ordinary normal version of the flow graph. So this is fairly straightforward. Why? That is because exactly one definition reaches every use. In the case of an ordinary flow graph, this is not so. We had even the reaching definitions problem. We solved using a data flow analysis. Here, for every variable, there is only one definition. That is the static single assignment. And therefore, whenever we have a usage of that particular value, we would be actually using the same variable. If there is another definition of the same variable, that will be renamed as another variable in the SSA form. That we have seen. So what do? We look at what is known as the definition use chain of the variable. This is another data flow analysis problem. Finding the definition use chain of a variable is another problem. And after solving the data flow analysis problem, for every definition, this is D, and here is a use. So U1, U2, and U3. 3 uses for the same definition, let us say. So they would all be linked. This is the DU chain of that particular variable. So if the DU chain is empty, right? If there are no uses, there is only a definition, but there are no uses for this definition, which is a variable in this definition. Obviously, if the variable is not used at all, but only defined, then that variable is a useless variable. So you can remove such variables and their definition statements. That is the way we do it. It's fairly easy here. If you have a statement such as x equal to y plus z, or x equal to y1 comma y2, and we delete it because of this reason, then care must be taken to remove the deleted statement from the DU chains of y and z, or y1 and y2 respectively. So that is a very important thing, right? If we delete x equal to y plus z, then this statement would have been a use of y and a use of z. So we must remove it in the corresponding DU chain also. Okay. So the same thing about x equal to phi of y1 comma y2. So in that sense, it's a fairly easy transformation, and of course it will retain the dominance property. So now we move on to a simple constant propagation to begin with, and then we will look at the conditional constant propagation. So simple constant propagation is easy to do. What do we do? You take all the statements in the program and put it into a statement pile, which is a queue. Put it into a queue. And while the queue is not empty, take a statement out of the queue and check. If the statement is of the form x equal to phi, and all these are constant, all the operations are constant, all the parameters are constant, then what it says is, irrespective of the direction we take to arrive at this phi box, the value that arrives is the same constant c. So we can get rid of the phi function and replace it by x equal to c. Fairly easy. Then second possibility, if s is of the form x equal to c, that could have happened because of this statement also, no problem. Then remove s from the program, and for all statements t in the du chain of x. So here I have x equal to c, and here I have various uses of x, right? u1, u2, u3. So in all these users, instead of x, I can replace it by c. That's what is constant propagation. So substitute c for x in t and simplify t. That is constant folding. Add this new statement into the queue again, because it has to propagate further. That's the reason we need to add it into the queue. We go on doing this until the queue is empty. That's all. Okay, but this is not conditional constant propagation. It is just simple constant propagation. It does not actually do much as far as conditions are concerned. We will see that. The second optimization is copy propagation. So a copy is of this form or this form. Just copying one variable into another variable. Obviously, it can be deleted and y can be substituted for every use of x. This is just like a constant propagation. Whereas copy propagation was we did not study it, but it is yet another data flow analysis problem in the ordinary flow graph domain. Okay, so it's much simpler to perform copy propagation and constant propagation using the SSA form. Any question? Now we move on to the constant propagation of the conditional variety. Well, it's a fairly intricate algorithm. So again, I can only give you an overview of how it happens with an example. But before that, the basis for the conditional constant propagation algorithm is the lattice of constants. So we assume that the lattice of the various numbers, that is all given here, 0, 1, 2, 3, minus 1, minus 2, minus 3, etc., is in this form, and the various constants such as minus 3, minus 2, etc., are incomparable. Well, obviously, when you have C1 and C2, which are minus 3 and minus 2, they are not the same. They are different. Right? And here are some of the operations on this abstract value. So if you have an undefined variable or a constant or not a constant, three possibilities, then the result would be, if you perform some operation, you may get undef and undef. The second operand is also undefined, then the result will also be undefined. If the second operand is a constant, this is again undefined. If the second operand is not a constant, then it is stronger. The result is not a constant. So that is very important. And you can see that for not a constant, all the three results are not a constant. The only thing which is very important for us is, if both the operands are constants, then we can do constant folding and the value is C1 plus C2. Okay. So the constant propagation lattice is used for interpreting the various operations in the flow graph during constant propagation. That's all I really wanted to emphasize with this picture. I will give you two examples. First one is a very simple example which we have already seen before. And the second one is a slightly more complicated example. For constant propagation, the static single assignment form is appended, or we add what are known as the SSA edges. What are these SSA edges? So, for example, here is the ordinary control flow graph, and here is the SSA control flow graph. The dotted edges are all known as the SSA edges. So, for example, there is an assignment of A1 equal to 10 here, and the dotted edge links to the block C5, where there is a usage of A1. So it's like a DU chain. So here is B equal to 20, and here is a usage of B. So this is a data DU chain. Similarly, this is also a DU chain. It is called an SSAH. Okay, it is nothing but a DU chain. So we start looking at C1, and now A1 equal to 10, nothing more. We just record it and keep it. Here we go to the next block, B equal to 20, right? Nothing more to do. We just keep it. Then comes the third block with a comparison. So in that, B has a constant value, which is already known to us, right? So we can evaluate it and say, yes, B same as 20? It is true. Evaluation happens for the condition here. And because the value turns out to be true, we need to retain only the S branch, and the no branch need not be kept in the flow graph at all. And then of course we have A2 equal to 10, A2 equal to 30. So that is processed. Then we come to the phi function, A3 equal to phi of A2. That is because this second parameter has been removed. Please observe that, right? So A3 equal to phi of A2 simply becomes A3 equal to A2 after constant, replacing the value of A2. So this becomes A3 equal to 30. Finally, we have D equal to A3. So the constant values propagate, and we use appropriate tables to keep these constant values. So after the constant propagation and folding happen, this is what we get. Okay. And we have not used these DU edges or SSA edges in our algorithm so far, but we will very soon use them in the next example. Here is a more complicated example. We have A1 equal to 1, B1 equal to 1, C1 equal to 0. And then we have a couple of phi functions in this. There is a condition with C2 less than 100. Then another condition B2 less than 20. And now we have a merge here, and therefore we have two phi functions. So it's a fairly complicated program. So let's see what happens. So we start with the processing of B1, and we note that A1, B1 and C1 have constant values 1, 1 and 0. That's all that happens during the processing of B1. Then we visit B2, right? So now the phi function receives a constant value for B1, a constant value for C1 also, right? So because we have, the important thing about the conditional constant propagation is, because we have not yet visited via this particular edge, we will assume that it is not present. We will assume that only this particular edge which we have seen is present. There is a good reason for it. We will see very soon. It will also do some dead code elimination. So if we assume that this edge is not present and only one edge, that is this, is present, then the phi function simplifies to phi of B1. Obviously, the first parameter is gone, right? So this parameter is gone because this edge is not even present according to us now. So phi of B1, B1 is 1, so can be evaluated as 1. Very easy. The similar argument holds for C2. Phi of C1 can be evaluated as C1, which is 0. So we have evaluated B2 and C2 here. Now, because C2 is a constant now, C2 less than 100 evaluates to 0 less than 100. Obviously, it is true. Now, we take only the true edge and the false edge is not taken at this time. If it is not necessary, we will never take it. So we come to the block B3 and visit it. If B2 less than 20, B2 happens to be a constant, which is 1 here, right? So B2 less than 20 will be true. If that is true, then we need to take only the true edge, and the false edge need not be taken at this time. So we come to block B5, which has B3 equal to A1, which is a constant, and C3 equal to C2 plus 1 is also a constant. So what happens? B3 equal to 1 and C3 equal to 1. These are again, constants which have been evaluated. Now there is only one edge which goes out of block B5, and that brings us to block B7. So again, because we assume that the second branch is not present, which has not been visited so far, the phi function simplifies. It becomes a phi function with a single parameter, and B4 can be evaluated as 1, phi of B3, B3 is 1, and C4 is phi of C3, which is also 1. The next branch which is taken happens to be the one from B7 to B2. So this is the only branch going out of B7, and therefore now we are forced to take this branch and go to B2. So in the second visit for B2, right, this block B2, both these are present, right? It is not that there is only one which is present. So it so happens that the value of B4 is 1. So along this direction also, along this edge, B4 gets 1, and B1 was already 1. So the value of B2 does not change. There is no change in the value of B2. But what about the C4, right? C4 has a value of 1 along this edge, and C1 has a value of 0 along this edge. Therefore, C4 being a 1 and C1 being a 0 cannot make C2 as a constant. It says it is not a constant, unknown, not a constant anymore. Once C2 less than 100, now we cannot say it is true all the time. It may be true or it may be false, and therefore we are forced to go along this direction also, take that edge also into consideration. And now something different happens. Because this block changes certain values, those values are actually transmitted using the SSA edge. So we can now directly visit the block B5 a second time. So during this time, now the value of B3 is 1. It was 1 before and it remains as 1. But the value of C3 is now actually, undefined. It's not known, right? Not a constant rather. It's not a constant anymore. So that value of C3 which has changed is transmitted using the SSA edge to the block B7. Okay. And of course, when we visit and this value is also transmitted to the block B6. So what happens is the block B6 has its value transmitted via the SSA edge, but we never had a chance to visit this by along the execution edge, right? We never did that before. Only the red ones are the execution edges. The black ones will not be visited during execution. Therefore, this block B6 now contains code which is useless. It need not be considered at all. And of course, B5 transmits its value to B7, and that will be taken care of here. So now the value of B4 is still 1, but the value of C4 becomes bottom, and that value is fed to the block B2 via the SSA edge. Now B2 is 1, C2 is not a constant, and the condition has either true or false. We don't know which one. And now the algorithm has not changed any value. B2 and C2 have remained the same. The condition value has remained the same. So it stops. So in this algorithm, we have removed the 2 instructions in the basic block B6. That is because we never get a chance to go along this direction. Okay. we always take this particular direction because this condition is always true. This is conditional constant propagation. Now we do a bit of simplification. We get this flow graph. Okay. Don't take this very seriously. Now we can do more simplification, elimination of dead code, elimination of trivial phi function, copy propagation, etc. You get a very simple flow graph. This is semantically equivalent to the original flow graph that I showed, this flow graph. It is equivalent, but it is a much simpler flow graph. And all this happened rather enabled by conditional constant propagation. This type of simplification is usually not possible without using the static single assignment form. It can be done only with SSA forms. This is the reason I showed you this example. Any questions so far? Okay. So the last topic, rather the last but one topic, is how to do global value numbering with SSA form. I showed you value numbering with basic blocks yesterday. Here, the same tables are used. We saw value num table, hash table, and all that, right? Name table. So the same tables are used here, but their scope is over the dominator tree, much bigger, right? It is not one basic block anymore. So therefore, you can catch more redundancies. Of course, there are other issues. We use the reverse post order of the DFS tree to process the dominator tree. This ensures that definitions are processed before use. Okay. And we also assume that copy propagation is carried out during value numbering, so that simplification can be done in lockstep. Here is an example. Again, this is an SSA form, and B1 dominates all the nodes in the tree, etc., etc. So it satisfies all the other requirements. So the scope of the tables will be over the dominator tree, and the processing order is the reverse post order on the dominator tree, which is B1, B3, B7, etc., etc. Okay. And there are lots of redundancies here, common sub-expressions which can be eliminated. Let us do it one at a time. So here is the DFS tree. Post order on the DFS tree is this, and the reverse post order on the DFS tree will be this. Okay. So here is the dominator tree. This is the reverse post order, right? On the DFS, this is the DFS tree, and here is the reverse post order. Okay. So the tables are enhanced, to accommodate the phi function. Okay. So that is something we need to worry about. So let us go through the example by looking at one block at a time, right? Okay. So we start processing B1. Okay. A1 equal to U1 plus V1, B1 equal to U2 plus V2. These are inserted into the tables, right? Then the order says process B3. So there is a new expression A3 equal to U3 plus V3. It is not the same as either U1 plus V1 or U2 plus V2. So this is a new expression which will be inserted into the table. Then we must process B7 according to this order, where we come to B5 equal to U3 plus V3, and that is a common sub-expression. Please observe that we are able to catch this because of the dominator table, the scope of the tables being over the dominator. So C3 equal to U3 plus V3 will also be replaced by A3. So this is the simplified set of quadruples. B5 equal to A3 and C3 equal to A. Sorry, these are the simplified equivalences. Okay. B5 is now equivalent to A3 and C3 is also equivalent to A3. We don't have to insert the expressions B5, C3 into the table again. We can simply say that we tag along A3 with B5 and C3. That's all. We don't have to do anything more than that. Then we process B6 according to this order. So we have U2 plus V2 here, right? So U2 plus V2 is defined here. And that can be used as a common sub-expression. See? So A6 is equivalent to B1 and C2 is equivalent to B1 again. So we can tag along A6 and C2 to B1 itself. Then we must visit B2, right, according to this order. So we have U2 plus V2, which is this. So this is done. And we have, U2 plus V2 here also. That is also B1. We have B2 equal to U3 plus V3 plus, please observe that this is not the same as this, not necessarily. Okay. So we will not assume that this U3 plus V3 in B2 and U3 plus V3 in B3 are equivalent. Nobody has told us so, right? One is in the true branch and the other was in the false branch. So we will not be doing anything about it. Then we process B5, which is again U2 plus V2. So we have B3 as equivalent to B1. Similarly, A4 equal to U2 plus V2 becomes A4 is equivalent to B1. Then we visit B8. Here we have A5 equal to phi of A4 comma A2. So A4 is equivalent to B1, right? And A2 is also equivalent to B1. So both the operands in the phi function become B1 and B1. So we don't have to keep the phi function at all. You can simply say A5 equal to B1 is equivalent to B1 now. Whereas for the second phi function, B2 remains as it is, B3 is equivalent to B1. No problem about that. That is here, right? So the phi function still remains here, whereas the phi function was gotten rid of in the previous one. Now, we call such phi functions which have the same operands as meaningless phi functions, and they can be eliminated. We come to B9, which is the last block to process. So A5, A6 and A3, they become B1, B1 and A3. A5 is equivalent to B1, right? And then A6 is equivalent to B1, whereas A3 remains as A3. So it's here. A5 is somewhere else. Yeah. Okay, here. Okay. Then B6 remains as it is. B1 remains as it is. But B5 is equivalent to A3. That we have done here. So these two were simplified a little bit with the copy propagation and all that. Now C4 becomes C1, C2, C3. C1 is B1, C2 is also B1, and C3 is A3, right? And C4 of phi B1, B1, A3 is same as A7, that is here. These two are the same. So why are we retaining two of them? C4 is redundant, so it can be eliminated. So after elimination, this is what we get, final SSA form. These two will be there, this will be there, this will be there, this 5 function and these 2 5 functions. All others can be eliminated. This will not be possible with ordinary flow graph. Only the SSA form can do this sort of global value numbering. Okay. Any questions so far? So I also have to mention what happens if there is a loop. Just assume that there is a back edge which is going to produce a loop. The problem is, here is U6 and here is U7, right? And U6 is phi of B1 comma A7 and U7 is phi of B1 comma C4. Let's assume that, okay, that it has. So these U6 and U7 are not even detected as equivalent, even though A7 and C4 in block 9 are equivalent. A7 and C4. They will become equivalent. We did that exercise earlier, you see, here. A7 and C4. We detected them as equivalent. But we visit this block B3 before we visit this block B9. And therefore, we are not able to utilize the effect of the equivalence detected by B9. So what happens? We simply say that they are not equivalent and they will remain. So some redundant phi expressions may remain even though in actuality they will be equivalent. So this is what happens because of the back edge. Okay. So back edges only water down the effect of value numbering, but not that they do any harm per se. Okay. Lastly, you may wonder whether the data flow analysis becomes easier or more difficult with the SSA form. At least for the liveness analysis, the SSA form makes life easy. Okay. So let me show you an example. Right. So here is an example, and we will take the variable I2. Okay. So we will take the variable I2 and trace its, we can take any variable, we'll just take the variable I2. So here is a usage of I2, right? And here is a definition of I2, right? So what we do is to look at all the, we start with the usage of I2. Here is of course one more. There are 2 usages of I2 and obviously just one definition of I2. It so happens that the definition of I2 dominates both the usages. That is the dominance property of the SSA form. So what we do is we start with the usages and then go up in the SSA graph until we meet the definition. And on the way, we include all the blocks that we get as the blocks where the variable is live. So let us do that for this I2. So we go to block B5 and we go to block B6, right? We still haven't got the definition of I2. Then we include B5 and B6 as blocks where I2 is live. Then we go to block B3. We still have not got the definition of I2. So we will include B3 also as the block where the variable I2 is live. Then we go to block B3 we hit the definition of I2. So we must stop here. So please observe that the output point or the out point of block B2, I2 is live because it is used everywhere here. Okay. But I2 is not live at the input point of the block B2. The same is true for this second usage I2. We go to block B2 immediately, right? So we include B3, B5, B6, right? And both the in and out points of the, and of course, of the blocks B3, B5, and B6. Then for B4, the in point, for B7 also, right, the in point, and for B2, the out point. So the variable I2 is live at the output point of B2, at the input point of B4, at both in and out of the block B3, in and out of block B5, in and out of block B6, and only the in of B7, right? So this is how we compute the liveness with the help of the SSA graph. It's a fairly simple strategy to start from the usages and go all the way to the definition. And since there is only one definition, and it will always be, met when we go up the SSA graph. That is what is said here. For each variable V, walk backwards from each use of V, stopping when the walk reaches the definition of V. This is what we did. Collect the block numbers on the way, and the variable V is live at the entry, exit, one or both, as the case may be, of each of these blocks. Right? So we already said this. For B6, B3, B4, it is in and out, and as the blocks are I2 is live. So this procedure works because the SSA forms and the transformations satisfy the dominance property, which I just stated here again. If the dominance property were not to be satisfied, then we would end up searching the entire SSA graph to get the corresponding definition. And this is precisely what goes wrong in the ordinary flow graph. And that is why we don't use something like this. We use a complete data flow analysis to compute the liveness on this. I should thank you for patiently listening to me.